Hello dear friends, welcome to a lecture on ring theory. Earlier we have studied the definition of ring, then types of ring, field, integral domain. In this lecture we shall study relationship between field and integral domain. There are results that we shall consider. First is every field is an integral domain, and then the second result we shall study is a finite integral domain is field. So we know that what is the meaning of field. Field is a commutative ring with unity in which every non-zero element has multiplicative inverse. And what about integral domain? Integral domain is a commutative ring without zero divisor, that is integral domain. And we have the first result as every field is an integral domain. This we shall prove. The proof this may be considered as result or sometimes a example also or problem also, but we shall write its proof. We shall consider R be a field. Let R be a field. Then we know field is commutative ring with unity in which every non-zero element has multiplicative inverse. Then R is a commutative ring with unity in which every non-zero in R, every non-zero element has multiplicative inverse. So that means let A is not equal to 0 and A belongs to R. Then there exists A inverse. We shall denote A inverse by this symbol. Then A inverse, inverse of A, multiplicative inverse, we shall denote by this symbol, belongs to R. Further, now let B belongs to R and AB is equal to 0. We have to prove it is an integral domain. We have to prove R is an integral domain. R is field, we have assumed. We shall prove R is integral domain. To prove R is integral domain, it is commutative is already there because field is commutative. We need to prove only it is without zero divisor. And we have studied earlier, without zero divisor means if AB is equal to 0, then either A is equal to 0 or B is equal to 0. Here we have assumed A is not equal to 0, and then if it is not 0, then its inverse exists, multiplicative inverse exists. So what we shall do here is AB equal to 0, therefore we shall pre-multiply both sides by A inverse. A inverse into AB is equal to A inverse into 0. Multiplication we shall not write now dot, AB means A dot B. And because it is associative, we shall write A inverse into A into B is equal to A inverse into 0 is 0, and by the property of 0. Then what is A inverse into A? That is identity element, and E into B is equal to 0. Generally identity element we denote by E, and that is or that can be considered as 1. Identity element is 1 into B, and identity for multiplication, and this implies B equal to 0. So thus AB equal to 0, this implies B equal to 0 if A is not equal to 0, and therefore AB equal to 0 and A is not 0 implies B equal to 0. Similarly, we can change the role of A and B. We shall consider B is not equal to 0, then B inverse exists, and then we shall have BA equal to 0, pre-multiply by B inverse, then we shall get A is equal to 0. Similarly, we have AB equal to 0. AB equal to 0 and B is not equal to 0. This implies A is equal to 0. And thus, if you combine these two results, AB equal to 0 implies either B equal to 0 or A is equal to 0. Thus, A into B is equal to 0 implies A equal to 0 or B equal to 0, where A and B are in R. And this proves that R is an integral domain. This is the ring without zero divisor. So, thus R is a ring without zero divisor. And therefore, R is an integral domain. And that means every field is an integral domain. So, this proves the result. R is field, R is integral domain. Now, second result we shall study is that can be considered as result 2 or a lemma. A finite integral domain is a field. The converse part of this, whether the converse is true, every integral domain is field, that is not true. But the converse is not true, but the converse, if you consider this integral domain as finite, then it becomes field. A finite integral domain is a field. Now we shall prove this. Let D be a finite integral domain. We shall denote the integral domain by D. D be a finite integral domain. Then it is a ring, commutative ring without zero divisor. That is by definition of finite integral domain. And so what we need to prove, it is a field, and to prove D is a field, we have to prove it has unit element and every non-zero element has multiplicative inverse. That is to be proved. So we have to prove that. To prove D is a field, we have to prove that the first result, D has unit element. D has the unit element 1, such that 1 into A, or that is commutative. See, finite integral domain is commutative. 1 into A into 1 is equal to A. For all A belongs to D. So this is the result that we have to first result we shall have to prove for field it has unit element, and second, every non-zero element has multiplicative inverse. Every non-zero element A has multiplicative inverse B. Inverse B, B not equal to 0 belongs to D such that AB equal to 1. So these two results we shall prove, and then we will get that D is field. Now D is finite integral domain, so we shall consider D contains n elements. Let let D has exactly n elements. Denoted by, and we shall denote it by x1, x2 and so on xn. D has these n elements. Further, we shall consider an element A in D again. Let A not equal to 0 and A belongs to D, be an element of D. Then obviously A will be one of these. So then we will multiply every element of this integral domain by A. So then if you multiply this each element by A, we will get x1a, x2a and so on xna, and these are also the elements of D, are also the elements of D, n elements of D. And this is because of closure property. See, these are the elements, n elements of D. These are also the n elements of D because of closure property. Why? x1 is element of D, A is element of D, therefore x1 into A is an element of D. Similarly, all these are the elements of D. So this is by closure property. Now we shall claim that these elements are all distinct. So we claim that x1a, x2a and so on up to xna are distinct elements of D, n distinct elements. Means none of them are equal. For or because, if suppose these are any two of these are equal, that is because if we may suppose xia is equal to xja, I is not equal to j, I and j are different and any two elements are equal, that we have considered. Actually we want to prove these are distinct, they are not equal. But what happens if they are equal? Then this implies, see, we can shift this element to this side and we have xia minus xja is equal to 0. Or that means we add the additive inverse on both sides and then we get here the right side as 0. And now by distributive property we have xi minus xj into A is equal to 0. And see, this implies because D is finite integral domain, D is integral domain, it is a ring without zero divisor, and therefore either this element is 0, xi minus xj is 0 or A is 0. But we have A is not equal to 0 here, A is not equal to 0 and therefore this must be 0. This implies xi minus xj is equal to 0, since A is not equal to 0 and D is an integral domain. Integral domain, this happens in integral domain because it is ring without zero divisor. And xi minus xj is equal to 0 means this implies xi is equal to xj. And this is a contradiction to I is not equal to j. When xi is equal to xj, if I is equal to j, but I is not equal to j, and therefore this is a contradiction. I is equal to j, and therefore these elements are distinct. Hence, or thus, the elements, thus x1a, x2a and so on, xna are n distinct elements of D. Now what we have is A is an element of D. So actually here what is happening is D, we have considered the elements. D contains exactly n elements, but we have written D in two ways. First we have written D as see, D is equal to, we have D has exactly these elements x1, x2, xn, and after multiplying this by A is one of these x1, x2, xn, we get another set of elements x1a, x2a and so on up to xna. And this happens in a finite integral domain. Now here the elements will be corresponding elements, not corresponding but in any sequence. These are n elements, these are n elements. They are either equal or they will be congruent to each other. And we have studied one such example as see, if you consider Z5, the ring of integers modulo 5, then these are the integers 1, 2, 3, 4. So it is an example of a finite integral domain. And if you consider any one element, say 2, and multiply all the elements by 2, so which elements we will get as 0 into 2, etc. This we will get 0 into 2, A is considered as 2, and then we multiply the elements by 2, 0 into 2, that is actually 0, 1 into 2, and then 2 into 2, 3 into 2, 4 into 2, or actually these will be 0, 2, 4, 6, 8. Now you see in Z5 or that may be denoted by J5, these elements and these elements are the same, because we have, this is under congruence modulo 5. So 0 is congruent to 0, 1 is congruent to 6 under modulo 5, and 2 is congruent to 2, again 3 is congruent to 8 under modulo 5, 4 is congruent to 4. So these are actually the same elements, and the same thing is happening here, though we have written x1, x2, xn, and here x1a, x2a, etc. The elements are the same here. These are exactly n elements in both the sets, and the relation is they are congruent to each other. So this is the case. Now what we have is A is in D. Now A belongs to D, therefore there exists some x, we will denote by xk, such that A is equal to xk into A. So then there exists some xk such that A is equal to, A is one of this, that means xk into A. Now we shall claim that this xk is the unit element, that is 1. So we claim that xk is the unit element. Now how to prove it as unit element? By definition of unit element, suppose y is another element, and then we have to prove y into xk is equal to again y, then xk will be unit element. For that purpose we shall suppose let y belongs to D. Therefore y is in D means in this set. We are considering now these elements. So y will be some xi into A for some xi. And now what is y into xk? Y into xk we will have as y is xi into A, and this is xk. See, because of associative property, we can write this as xi a into xk. And what is a into xk? Because this is commutative. This is a integral domain. Integral domain is commutative ring, and therefore we can have a is equal to xk. A or is same as a into xk. So a into xk is a. So this is xi. And what is xi into a? That is y. So thus we have y into xk is equal to y, or therefore y into xk is equal to, it is commutative, that is xk into y is equal to y. And this shows that thus xk is the unit element, and that is 1. Xk is the unit element of D. So this is what we have to prove the first condition. It contains unit element. Now what is the second condition? It has every non-zero element has multiplicative inverse. That is that follows easily. See, second part, this proves 1. Now next, 1 belongs to D. 1 belongs to D means 1 is among these elements, one of these elements. So therefore it is multiple, and every element of D is multiple of A. Since every element of D is multiple of a we have 1 is equal to, 1 is multiple of A, 1 can be written as B into A, where B is sum of xi. Sum x1, x2, etc. we can denote it by B, and thus we have 1 is equal to BA or AB. And this shows that A and B are multiplicative inverses, and A we have chosen earlier, A is not equal to 0, where A is not equal to 0 belongs to D. And this shows that, or this proves second property. This proves second, means for A there is multiplicative inverse B. A and B are inverses of each other, and that means non-zero element has multiplicative inverse, and thus D is a field. D, or which is a finite integral domain, is a field. So this is the relation between field and integral domain. Every field is an integral domain, but not every integral domain is field. If it is finite integral domain, then it becomes field. So in this lecture we have studied relation between field and integral domain. The remaining part we shall continue in our next lecture. Thank you.